So we're looking at alternating current here. It's very useful to compare two different things as a way of learning a new thing or slotting it into your current knowledge base. This is alternating current, roughly speaking, very roughly speaking. We're looking at the voltage as it changes over time. And this is direct current, without the wobbly bits, but direct current, if we're considering a circuit, it just goes around in one direction continually. Okay, so it's always going in the same direction. Alternating current is going back and forth and back and forth and back, so it's continually shifting and going backwards and forwards throughout a circuit. Okay, how does that work in terms of current and voltage and so forth? Well, your peak voltage times by some modifier will give you your voltage at any particular point in time. So we need an equation that represents the change in voltage according to time, or according to the change in time. So that voltage at any one point in time is going to be our maximum voltage. And since this is a sine curve, it's a sine modifier, and it's times by the time. Usually there's something rotating to produce this, so we have to use an equation to get our angle as omega times t. I'm not going to get into the main details, but omega is your angular velocity, or angular rotation, the change in the angle in radians over time, and rearranged we get this, and this is what we're going to use. So V equals V max sine omega t. As I said, I don't want to dwell on that. You have the same thing with current, so current would be I max sine omega t, because the current and the voltage follow each other for just a standard plain and normal circuit. Okay, so that's just the basic DC comparison. If we're looking at how we generate alternating current, it's not too different from how we generate DC. Let's really quickly look at how we generate DC. This is our north and our south magnetic poles, and we have a coil of wire inside. We force the rotation, and so as we rotate this inside the field, we produce a current flow. With DC, or pseudo DC, where we're trying to produce, how to say, it's naturally going to vary according to time, because as the wires and the coil are moving parallel to that north-south magnetic field. So let's draw this here. If we have a wire that's moving parallel to the field, there will be no force on the charges inside that wire to drive a current flow. It's only when, if you consider the circular path that a single piece of this wire follows, that circular path, as it's going upwards and cutting the field, or downwards and cutting the field, it's going to apply a force to the charges, driving them around the circuit, and those forces are according to right-hand slope rules and all that kind of stuff, or different rules for generator depending how you want to use it. The real, how we started with this is that it'll vary between a maximum and 0, and then back to maximum according to this circular path moving through the field. It's only when it's cutting the field perfectly that you get a maximum, and you get 0 when it's going parallel with the field in the direction of movement, and somewhere in between it'll be a function of this sine thing. But we want to get them all pointing upwards. That's roughly the how a DC generator would work. Most people don't use DC generators, but it's important to look at this to understand the concepts. For a DC generator, we would have a split ring commutator, so that this piece of wire is always driving the current in the same direction around the circuit that would be attached. that's our load resistor. So we want this, because as you see over here, let's go back to a different colour so we can see, when that piece of wire is moving upwards through the field, current will flow one way through it, and then when it moves downwards, and so it's over here moving downwards, it'll produce a current in the other direction. You can, the direction of the wires move changing with respect to the magnetic field. Splitting the ring here provides a way for that to always produce current going in the same direction around the circuit, and that produces this changing. It's like a sine wave with all the negative parts flipped and put onto the top. Okay, now this is one way to produce DC, but AC has a slightly different setup where oh dear, I feel like I think I just lost everything. I don't know if you lost everything, but I did on my sheet, so I'll have to redraw it. But let's just move down here in case I'm drawing over the top of anything. Here's our setup again with our ring in the middle. This time one side is attached to the same side all the time, so there's a point of contact with our ring here, and as the coil rotates it maintains contact with that ring there. Then we have another ring over here and contact is maintained here. So this way, this is always this means we're going to get a shifting, if we were to stick a voltmeter across there, we're going to get a shifting voltage. Okay, you can ponder a little bit more why that is if you're not sure, but we're a bit limited for time on the video. So now I've lost everything again. We're having a few bugs within Explain Everything, which was the program I used to do this. In any case, we're generating AC using that. You can use a rectifier to produce proper DC, and that'll be the subject of another video, I think. Measuring AC is quite important, so we'll look at that. If you were to stick a analog meter, analog voltmeter, that's one of these ones, and it's got the needle that moves, that would shift back and forward for your alternating current. If you had your zero somewhere in the middle, then it would shift back and forward either side of that. If you were to use a digital multimeter with your selector, there you go, if you were set on DC voltage with your digital multimeter, you would read 0, because the positive and negative parts of that line are cancelling each other out, so whatever positives you get are cancelled out by the negatives there, and your average is 0. However, if you set your meter to AC voltage, you would actually get a reading, and you would get what we call a DC equivalent, which is very useful. It's what we would call the RMS voltage. So how we arrive at the RMS voltage is, if this is your sine curve showing the time, the voltage against time as the voltage changes. For a sine curve, this is pi, and this peak is 1, and interestingly enough the area under there is 2. So if you like, you've got a whole lot of these humps with area under them of 2, 2, 2, 2, 2. We want to find a DC equivalent that just gives us a nice steady average, and this turns out to be more useful for power calculations and things like that. And if you imagine each block is a square with area 2, the sides of that are going to be square root of 2 and square root of 2, and that gives us an easy way to work out what that average is going to be. It's going to be the peak divided by the square root of 2, and that works out to be around about 0.7 times the 0.7 times the max. Okay, because 0.7 is about 1 over the square root of 2. another way to look at it, just to give you this concept very clearly, this area under here is 2, and the length of this side is 3.141592, it's pi, and or p if you're pronouncing it properly if you're Greek. So the height of that has to be around about 0.7 to make the area under that equal to 2. Okay, if that's, yeah, just for multiplying it out. I think that's kind of cool. Anyway, so way to convert is to take your max and divide it by the square root of 2. Works the same for the current. If you want your peak current or your maximum current, just to find the RMS value, divide by the square root of 2, and that gives you a very useful value. If you're calculating power, you would use your two RMS values, I times V, but they'll both be RMS. Final thing, this video is very long, but final thing is, whenever you see a value in a textbook or anything, you can assume they've used the digital multimeter to measure it, which means it's going to be an RMS value, okay, an average value. So in New Zealand our mains are 240 volts AC, and the peak is actually that's our RMS value, so the peak is actually times by 1.4, sorry 1.4 not 0.14, to get you around about whatever that is, 350 odd.